What if everything we know, every star, every galaxy, every law of physics, is just one tiny fragment of an unimaginably vast cosmic tapestry? Imagine for a moment that our universe isn't the only one. That beyond the edges of what we can see, there are countless other realities, each with its own rules, its own history, its own version of you. This isn't science fiction, it's a real scientific possibility, one that forces us to ask an even deeper question. Is our universe here by sheer chance, or was it designed to be exactly as it is? Think about the odds, the constants of nature, the speed of light, the strength of gravity, the charge of an electron are so precisely tuned that if any one of them were even slightly different, life as we know it wouldn't exist. Stars wouldn't form, atoms wouldn't hold together, the universe would be a cold, empty void. So how did we get so lucky? Some scientists argue it's pure coincidence, that in an infinite multiverse, every possible configuration of reality exists somewhere, and we just happen to live in the one where everything lines up perfectly. Others see something more profound, evidence of a deeper intelligence, a cosmic blueprint fine-tuned for life. This is the heart of the multiverse debate, a clash between randomness and intention that stretches our understanding of existence itself. And today, we're diving into the heart of it. We'll explore the mind-bending theories of parallel worlds, the eerie precision of our universe's laws, and the haunting question that lingers over it all. Are we here by accident, or is there something or someone behind the curtain? Strap in, because by the end of this journey, you might never look at reality the same way again. Picture a vast, churning ocean of possibility, an endless expanse where new universes bubble up and drift apart like foam on the waves. This isn't fantasy, it's one of the leading scientific visions of the multiverse. At its core, the idea hinges on two powerful theories, quantum mechanics and string theory. Quantum mechanics tells us particles can exist in multiple states at once until observed, as if reality itself hesitates before choosing a path. But what if every possible outcome does happen, just in separate, branching universes? That's the many worlds interpretation, where every decision you've ever made spawns new realities where alternate versions of you live out the roads not taken. Then there's string theory, which suggests our universe might be one tiny membrane floating in a higher dimensional space, occasionally colliding with others like soap bubbles in a sink. These brain universes could have entirely different laws of physics, some with gravity 100 times stronger, others where time runs backward, and the most mind-bending part. We might never detect them directly because they exist beyond the reach of our cosmic horizon, like distant ships vanishing into fog. Even the Big Bang might not have been a one-time event. Inflation theory proposes that space-time expands exponentially, creating pocket universes in its wake, each a self-contained cosmos with its own unique constants. Think of it like a cosmic bakery where the oven never turns off, endlessly baking new universes with slightly different recipes. Some are dense and collapse instantly, others are barren, lifeless voids. But a rare few, like ours, have just the right ingredients for stars, planets, and life. This shakes the very foundations of how we see reality. Instead of a single, finely tuned universe, we might be living in one lottery ticket among countless losers, a statistical fluke in an infinite cosmic draw. Or, as some physicists argue, this dizzying plurality could be the key to answering why our universe seems so improbably perfect for life. The multiverse doesn't just expand our map of existence, it forces us to rethink whether the word coincidence even applies when every possibility is out there, somewhere, playing out in parallel. So how exactly could multiple universes exist? Scientists have theorized several compelling possibilities, each more mind-bending than the last. Let's start with the simplest, level 1. Imagine space stretching endlessly beyond what we can observe, an infinite cosmic ocean where every possible arrangement of matter repeats itself over and over. Far beyond our observable horizon, there might be identical copies of you reading identical copies of this script, living on planets indistinguishable from Earth. It's not magic, it's probability. In an infinite expanse, even the most unlikely events must happen somewhere. Then there's level 2, bubble universes. Picture a boiling pot of water with steam bubbles constantly forming and popping. Now replace the water with space-time itself. According to eternal inflation theory, our universe might be just one bubble in a frothing sea of others, each with its own unique physics. Some bubbles might have stronger nuclear forces, making stars burn out in seconds. Others could be so warped that time loops back on itself, the terrifying beauty. These bubbles never touch, they drift apart forever, sealed off by walls of expanding space. Level 3 takes us into the quantum realm. Every time a particle has a choice, like whether to spin left or right, quantum mechanics says it does both until observed. The many worlds interpretation takes this further. Every possible outcome actually happens, splitting reality into infinite branches. Missed a train today. Somewhere, a version of you caught it, chose coffee over tea. Another you is sipping that Earl Grey right now. It's not science fiction, it's a direct consequence of the math behind quantum theory. But level 4 is where things get truly surreal. What if every possible mathematical structure exists as a physical universe? Not just variations of our laws, but realities where 2 + 2 = 5, where shapes have 4 dimensions, or where time runs in circles. In this view, our universe isn't special, it's just one equation in an infinite cosmic library. A triangle drawn on paper isn't just a representation, it's a doorway to a universe where triangles are reality. These aren't wild guesses, they're grounded in cutting-edge physics. The chilling implication, if even one of these levels is real, everything might be far grander and stranger than we ever dreamed. Now consider the delicate balance holding our universe together, not just in broad strokes, but down to the razor's edge precision of its fundamental constants. Take gravity, for instance. If its strength were even slightly weaker, stars wouldn't exert enough pull to ignite nuclear fusion, leaving the cosmos dark and lifeless. Stronger stars would burn too fiercely, collapsing into black holes before planets could form. It's like balancing a pencil on its tip for billions of years, except the pencil is all of existence, and the slightest tremor would send everything tumbling into chaos. Electromagnetism is just as precarious. The force binding atoms together is fine-tuned to an astonishing degree. If it were marginally stronger, electrons would clamp onto nuclei so tightly that chemical reactions, the foundation of life, could never occur. Weaker atoms would fly apart like dust in the wind. Even the ratio of protons to electrons is eerily perfect. A fraction more or less, and the universe would be dominated by crushing radiation or featureless plasma. Then there's the cosmological constant, which governs the expansion of space itself. When scientists calculated its expected value based on quantum theory, the result was off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. Yet somehow, the actual value is just right enough to keep galaxies from tearing apart, but not so much that the universe expands into a lifeless void. The odds of this happening by chance are like flipping a coin and getting heads 10,000 times in a row. Even time plays its part in this cosmic ballet. The rate at which the early universe cooled allowed matter to clump into galaxies instead of dispersing into nothingness. A faster cooling would have left only hydrogen, slower, and heavy elements, the building blocks of planets and life, would never have formed. Everywhere we look, the numbers are so exact, so unlikely that it begs the question, are we staring at the ultimate lucky break or the fingerprints of something deeper? Some argue this precision points to a multiverse where countless universes with random constants exist, and we simply inhabit the one where everything lined up. Others see it as evidence of intentional design, a universe crafted with life in mind. Either way, the numbers don't lie. We're standing on a knife's edge, surrounded by a reality that shouldn't be, yet is. The moment you step back and ask why the universe seems tailor-made for life, you bump into one of the most provocative ideas in cosmology, the anthropic principle. At its core, it's a simple observation: we exist, so the universe must have properties that allow our existence. But dig deeper, and it fractures into two starkly different interpretations. The weak anthropic principle is the less controversial cousin. It's a reminder that our observations are inherently biased. We couldn't possibly measure a universe that didn't permit life because we wouldn't be here to measure it. Think of it like a puddle marveling at how perfectly its edges fit the hole it's in. The puddle doesn't realize the hole came first. It's just congratulating itself on the coincidence. But the strong anthropic principle takes this further, arguing that the universe must have properties that allow life to arise, as if life itself were a baked-in requirement of reality. Proponents see this as evidence of something deeper, perhaps a multiverse where only life-friendly universes count, or even a cosmic designer who set the dials intentionally. Critics fire back. This veers dangerously close to tautology, like saying, the universe is hospitable because we're here to say it's hospitable. It's the difference between noticing a locked door and insisting someone must have locked it for a reason. The debate gets even thornier when you consider how easily observation warps our perspective. If the cosmological constant were slightly larger, galaxies would never have formed, but we wouldn't be around to lament their absence. Our very presence filters what we can perceive, like survivors of a shipwreck assuming all voyages end happily because they never hear from those who sank. This observer bias forces us to confront an uncomfortable truth. Our universe might not be fine-tuned for life at all. It might just be the only roll of the dice where life could emerge and ask the question. Physicist Brandon Carter, who coined the term, framed it as a cosmic reality check, but the implications ripple far beyond physics. If the weak principle holds, we're accidental beneficiaries of indifferent laws. If the strong principle is right, we might be part of something intentional, a universe that expects us. Between these two poles lies an abyss of unanswered questions. Is our existence a fluke or a foregone conclusion? The anthropic principle doesn't solve the riddle, it just sharpens the stakes. After all, every answer we propose is filtered through the very bias we're trying to escape. The numbers are staggering, like winning the lottery every second for 1 billion years, except the prize is existence itself. Consider gravity. Tweak its strength by just 1%, and stars would either never ignite or burn out in cosmic blinks. Not 1% weaker or stronger, 1%. That's the margin between a universe teeming with galaxies and one that's eternally dark. The same razor-thin precision applies to the nuclear forces binding atoms. A fraction weaker, and hydrogen, the fuel of stars, wouldn't fuse. A fraction stronger, and all hydrogen would have burned up in the Big Bang's fireball, leaving nothing but sterile helium. These aren't just narrow parameters, they're surgical. Yet some physicists push back, arguing these coincidences might be illusions, artifacts of our incomplete understanding. Imagine a child marveling at a stoplight, convinced it magically turns green just as their car approaches. They don't see the hidden timer synchronizing the system. Could our universe's fine-tuning be similar? String theory, for instance, suggests the constants we measure might not be fundamental but emergent, like the temperature of a room arising from countless chaotic molecular collisions. If higher dimensions or undiscovered physics govern these values, what seems impossibly precise might be inevitable. Then there's the dark matter puzzle. We can't directly detect it, yet its gravitational grip shapes galaxies. What other invisible forces might be nudging the universe's dials? Some models propose a relaxation mechanism, where early cosmic turbulence smoothed extreme values into life-friendly ranges, like a river carving its own path over millennia. Others speculate our constants aren't fixed but evolving, with universes naturally selecting stable configurations over eons. But the boldest counterargument comes from quantum cosmology. What if the laws themselves are mutable? In the quantum foam of the early universe, physics might have been a kaleidoscope of trial-and-error configurations, with only the stable combinations surviving long enough to spawn observers. It's Darwinism on a cosmic scale, no designer needed, just endless iterations until something sticks. The irony, both sides appeal to the unknown. Fine-tuning advocates sea gaps as evidence of intent. Skeptics see them as frontiers waiting to be crossed. Either way, the debate forces us to confront a humbling truth. Our universe's recipe is still missing ingredients. Until we find them, we're left staring at the numbers, wondering if they're a cosmic signature or just the first line of a much longer equation. Here's how infinity changes everything. If you had a casino with an endless row of slot machines, each set to random odds, it wouldn't just be likely that one eventually hits the jackpot, it would be guaranteed. Now replace those slot machines with universes, each spinning its own unique set of physical constants. In an infinite multiverse, the odds stop being odds and become inevitabilities. A universe where gravity crushes atoms into dust, it's out there. One where electromagnetism is too weak to form molecules, it exists too. But buried in that cosmic noise is a single machine that lands on the perfect combination, the universe we call home. This isn't just speculative math. Think of Earth's history. Dinosaurs ruled for 160 million years before an asteroid wiped them out, clearing the stage for mammals. That catastrophe was wildly improbable, yet in the vastness of geologic time, the unlikely became unavoidable. The multiverse applies the same logic to reality itself. With infinite tries, even the most absurdly precise conditions, like the exact charge of an electron or the mass of a proton, must occur somewhere. We're not lucky, we're statistically inevitable. Critics push back, arguing this turns science into a cosmic shrug. Anything can happen somewhere, so why bother explaining? But proponents counter that it's the opposite. The multiverse demands explanation. If we accept that our universe's constants are fixed and unchangeable, their perfect balance seems inexplicable. But if they're random variables in an endless ensemble, suddenly the mystery isn't, why are we here? But where are the others? The answer might lie in the very nature of infinity. Most universes would be barren, their laws too hostile for even atoms to form. We could only ever wake up in the rare one that allows us to wake up at all. The real twist, this idea flips fine-tuning on its head. Instead of a universe meticulously crafted for life, we might be living in the one that barely scraped by. Imagine a million flawed paintings smudged, torn, or blank, with a single intact masterpiece hidden among them. The artist didn't intend for it to survive, it just got lucky. That's the multiverse's sobering implication. Our existence might not be a grand design, but a fleeting accident in a sea of cosmic chaos. And yet, here we are, the accident that thinks, wonders, and asks why. For all its grandeur, the multiverse theory isn't without its critics, and their objections cut deep. At the heart of the skepticism lies a fundamental question. If we can't observe, test, or even interact with these other universes, does the idea belong in science at all? Nobel laureate David Gross dismisses it as a retreat from empirical rigor, calling it a dangerous undermining of what we mean by science. His concern isn't just academic, it's about the very rules of the game. Science thrives on falsifiability, the ability to prove an idea wrong. But how do you disprove the existence of something forever out of reach? A universe beyond our cosmic horizon might as well be a castle in the clouds, beautiful to imagine, impossible to touch. Even proponents acknowledge the problem. MIT's Max Tegmark, a vocal multiverse advocate, admits, the bitter pill is that most of reality might be forever hidden from us. Yet he argues that dismissing it outright ignores the math equations that predict multiple universes as naturally as Newton's laws predicted Neptune. The tension here is razor sharp. Is the multiverse a bold extension of physics or a philosophical Hail Mary? Critics like physicist Paul Steinhardt see it as the latter, accusing it of being a theory of anything that explains everything but predicts nothing. If every possible outcome exists somewhere, how do we distinguish meaningful patterns from cosmic noise? Then there's the metaphysical cop-out charge. By invoking infinite universes to explain fine-tuning, are we sidestepping deeper mysteries? Philosopher of science Karl Popper warned that explanations which account for all possibilities ultimately account for none. It's like saying a broken clock is right twice a day, technically true, but useless for telling time. Some physicists, like Sabine Hossenfelder, argue this approach stifles creativity. If we accept anything can happen, we stop looking for the underlying mechanics that might make our universe inevitable. But the debate isn't just about methodology, it's about storytelling. The multiverse offers a narrative where humanity isn't special, just statistically probable. To some, that's liberating. To others, it's bleak. As cosmologist George Ellis puts it, science should aim for more than just consistency with observation. It should strive to tell us why one consistent story is truer than another. The multiverse, in his view, fails that test by offering infinite stories with no way to choose between them. Yet for all the criticism, the theory persists, fueled by gaps in our understanding. Maybe the multiverse is a placeholder, a scaffold for ideas we're not yet equipped to test. Or perhaps, as skeptics fear, it's a cul-de-sac, dazzling but ultimately leading nowhere. What's clear is this: until we find a way to peek beyond the curtain of our universe, the debate will rage on, a testament to science's greatest strength and its greatest frustration, the refusal to confuse comfort for truth. Long before multiverse theories or quantum physics, humanity grappled with the same awe we feel today. The uncanny sense that the universe seems too orderly to be accidental. Enter the teleological argument, one of philosophy's oldest and most persistent ideas. At its core, it's astonishingly simple. When you see a watch, you assume a watchmaker. So when we observe the intricacy of life, the precision of planetary orbits, the fine-tuned constants of physics, doesn't that imply a cosmic watchmaker too? Thomas Aquinas laid the groundwork in the 13th century with his fifth way, pointing to natural phenomena like the purposeful motion of celestial bodies. His reasoning, things without intelligence, like stars or seeds, don't move toward goals unless directed by something that does have intelligence. Fast forward to the 18th century, and William Paley's famous watchmaker analogy sharpened the point. Stumble upon a rock, he said, and you might think nothing of it, but find a watch with its gears and springs working in harmony, and you'd instantly infer a designer. For Paley, the eye, with its lens, retina, and perfect focus, was nature's watch, too complex to be random. Modern intelligent design advocates revive this thread with biochemical examples. Take the bacterial flagellum, a microscopic outboard motor some bacteria use to swim. Its intricate parts are propeller, rotor, and stator. All need to exist simultaneously for it to function. Remove one piece and the system collapses. Proponents argue this irreducible complexity can't be explained by gradual evolution. It screams intentional engineering. But critics pounce with a devastating counter. If the universe requires a designer who designed the designer, this isn't just wordplay, it's a fundamental flaw in the logic. Any being capable of crafting reality would presumably be even more complex than the cosmos itself, kicking the mystery up a level without solving it. As Richard Dawkins frames it, invoking a creator merely postpones the question of origins. Philosopher David Hume took this further centuries earlier, dismantling the watchmaker analogy itself. A watch is nothing like a universe. We've seen watches made, but we've never seen universes crafted. And what if nature's design is just the result of endless trial and error, like a sculptor chiseling away marble until form emerges? Darwin's theory of evolution later provided the mechanism Hume lacked, showing how complexity can arise from simplicity over eons, no blueprints required. The debate rages because it's about more than science, it's about the stories we tell ourselves. Design arguments offer narrative comfort, a universe with meaning baked in. But they also risk what philosopher Daniel Dennett calls skyhook thinking, reaching for miraculous explanations instead of grappling with the hard, incremental work of natural processes. Yet even skeptics admit the haunting beauty of the question. Whether you see fine-tuning as divine craftsmanship or a multiverse's brute force statistics, one truth remains: we're here in a universe that allows us to ponder its existence. And perhaps that's the most astonishing coincidence of all. Now imagine peeling back another layer. What if the multiverse isn't just a cosmic accident or a divine blueprint, but something far stranger? Lines of code in an unfathomably advanced simulation. This is the simulation hypothesis, where the eerie precision of our universe's constant starts to look less like fine-tuning and more like debugging. Philosopher Nick Bostrom framed it as a trilemma. At least one of these statements must be true. 1. Almost all civilizations at our level go extinct before becoming technologically mature. 2. Virtually none choose to run ancestor simulations, high-fidelity recreations of their past. Or 3. We're almost certainly living in one of those simulations right now. The logic is unsettlingly clean. If future civilizations can simulate conscious minds, and if they have even a modest interest in exploring their history, the number of simulated realities would dwarf the single, base universe. Statistically, the odds tilt overwhelmingly toward us being among the simulations. Elon Musk famously summed it up: the odds we're in base reality are 1 in billions. Suddenly, the multiverse's infinite branches might not be parallel worlds but server clusters in some vast computational matrix, each universe a separate instance running its own physics engine. This reshapes how we interpret fine-tuning. In a simulation, constants aren't brute facts but parameters, adjustable settings like gravity or the speed of light, dialed in by whatever or whoever booted up the program. Think of a video game designer tweaking variables until the world feels believable. Too much friction and players can't move, too little and they float away. Our universe's Goldilocks precision starts to seem less miraculous and more like intentional calibration. But the simulation argument isn't without cracks. Critics point out it's a modern twist on old philosophical puzzles, Descartes' evil demon or Boltzmann's brain, where reality might just be an elaborate illusion. And while it's fun speculation, there's no empirical way to test it yet. Some physicists, like Seeler's bean, suggest hunting for glitches, rounding errors in energy levels at ultra-high resolutions, like pixels in a rendered universe. Others propose that quantum indeterminacy might be the system's way of saving processing power, only calculating outcomes when observed. The eerie overlap with multiverse theories is hard to ignore. Both dissolve the uniqueness of our reality, one into infinite physical worlds, the other into coded constructs. Both answer fine-tuning by making our universe one of countless iterations. And both force us to confront the same existential question: does it matter if we're in a simulation or a multiverse? After all, the stars still burn, the laws still hold, and the mystery remains. Whether we're cosmic accidents, lines of code, or something beyond our current imagination, one truth persists: we're here asking the question, and maybe that's the most remarkable fine-tuning of all. Quantum mechanics doesn't just describe reality, it shatters our most basic assumptions about how reality works. Take the observer effect, the bizarre idea that particles don't settle into definite states until someone or something measures them. It's as if the universe waits, holding its breath, until you look at it to decide what it actually is. In the famous double-slit experiment, electrons behave like waves when no one's watching, creating an interference pattern on a screen. But the moment you set up a detector to see which slit they pass through, they snap into crisp, particle-like behavior. The act of observation itself seems to force nature to pick a side. This isn't just laboratory curiosity, it's the foundation of wave-function collapse, the moment quantum possibility crystallizes into concrete reality. Schrödinger's cat drives the point home with grim elegance. A cat in a sealed box, its fate tied to a quantum event, exists in a surreal superposition, both alive and dead, until someone opens the lid and collapses the probabilities into a single outcome. But here's where it gets dizzying. If observation defines reality, does that mean conscious observers are creating it? Could the universe itself be a tapestry of possibilities, woven into existence by the very act of being perceived? Some interpretations take this even further. The von Neumann-Wigner theory suggests consciousness itself might be the trigger for collapse, implying that without a mind to observe it, reality remains a fog of unrealized potential. Imagine a tree falling in a forest with no one around. Does it even make a sound? Or does it hover in quantum limbo until some form of awareness interacts with it? This isn't just philosophy, it's a direct challenge to our understanding of causality, time, and the nature of existence. Critics push back hard. The many worlds interpretation sidesteps the observer problem entirely by arguing there's no collapse, every possible outcome happens, branching into parallel realities where the cat lives in one universe and dies in another. No conscious observer required, just an endlessly splitting cosmos. Others propose that collapse is a physical process like decoherence, where interactions with the environment, not consciousness, solidify quantum fog into classical certainty. A dust grain or a photon could do the job as easily as a human brain, yet the question lingers like smoke in a closed room. If observation shapes reality, how far does that influence extend? Could the collective attention of billions of conscious beings, human or otherwise, be tuning the universe's constants into focus, like a radio dial finding the right frequency? Or is this just an illusion, a quirk of quantum math mistaken for something mystical? One thing's certain, quantum mechanics doesn't just describe the rules of reality. It forces us to ask who or what is playing the game. Dark matter and dark energy, two phrases that sound like science fiction, but represent the most humbling reality in modern cosmology. We don't know what 95% of the universe is made of. Think about that. All the stars, planets, and galaxies we can see, the entire tapestry of light and matter we've spent centuries mapping, are just 5% of existence. The rest, a cosmic blind spot, invisible yet exerting undeniable force. Dark matter binds galaxies together like unseen glue, while dark energy stretches space itself apart at an accelerating rate. But here's where it gets wild. Could these mysteries be clues to something even bigger, like traces of other universes bleeding into ours, or hidden layers of design we're only beginning to sense? Picture an iceberg, the visible universe. Everything we detect with telescopes and particle colliders is the tip poking above the water. Beneath the surface lies the vast, uncharted bulk, dark matter's gravitational whispers, dark energy's relentless push. But what if that submerged mass isn't just unknown physics? What if it's evidence of a deeper structure where our universe brushes against others? Some theories suggest dark matter could be particles from a parallel reality, drifting through dimensions we can't access. Others propose dark energy is the tension between colliding brains in higher dimensional space, like ripples from a cosmic shore we'll never see. The math hints at tantalizing possibilities. In certain string theory models, gravity, uniquely feeble compared to other forces, might leak into our universe from another, explaining why dark matter's pull feels so ghostly. Alternate universes with slightly different physics could imprint their presence on ours as anomalies in the cosmic microwave background, like fingerprints on a window. Even the absurdly small but non-zero value of the cosmological constant dark energies calling card might be a fossil from an ancient multiverse collision, a scar left by a long-vanished sibling universe. Yet the most provocative idea isn't leakage, it's engineering. Could dark matter and energy be the artifacts of a universe fine-tuned not by accident but by intent? Philosopher Nick Bostrom once mused that advanced civilizations might rearrange stars to communicate. What if they've manipulated the fabric of space-time itself? Dark energy's precise balance strong enough to drive expansion but weak enough to allow galaxy formation could mirror the dials of a machine calibrated for life. It's a staggering thought. The invisible 95% isn't a void, but the scaffolding holding up the stage we call home. Of course, skepticism is healthy. Critics argue these ideas stretch science into speculation, that dark matter could simply be undiscovered particles, and dark energy an emergent property of space we don't yet grasp. They're right to demand evidence, but history shows that every cosmic revolution from heliocentrism to quantum mechanics began as heresy. The truth may be stranger than we dare imagine. After all, if the universe has already proven 95% of itself is hidden from view, why wouldn't the remaining mysteries defy expectation? Whether through multiverses, design, or physics we've yet to dream of, one thing's certain: the darkest parts of the cosmos may hold the brightest revelations. Suppose a single, disembodied brain complete with memories, thoughts, even the illusion of a body suddenly flickered into existence in the empty void of space. Not attached to anything, not born of anything, just poof, a conscious mind hallucinating an entire reality from scratch. That's the nightmare logic of the Boltzmann brain paradox, a thought experiment so bizarre it either unravels multiverse theories or accidentally proves the universe must be fine-tuned. Here's how it works. In an infinite, chaotic multiverse, random fluctuations can, given enough time, spontaneously create anything, from a single atom to an entire galaxy. Statistically, it's far easier for a lone, self-aware brain to form by accident than for an entire ordered cosmos to emerge. The odds are still astronomically low, but infinity doesn't care. Over endless time, Boltzmann brains named after physicist Ludwig Boltzmann would outnumber ordinary minds like ours by an unimaginable margin. So why don't we experience reality as fractured hallucinations in a void? Why does the world feel so stable, so real? This isn't just a sci-fi horror scenario. It cuts to the heart of cosmology's biggest questions. If the multiverse is truly infinite and random, our coherent existence becomes unlikely, an outlier in a sea of chaos. Some theorists argue this absurd conclusion exposes a flaw in multiverse logic. Maybe reality isn't random at all, but structured in a way that prevents such freak occurrences. That structure could be evidence of fine-tuning, a universe calibrated to produce stable, embodied minds rather than fractured ghosts, but the paradox has teeth on both sides. If Boltzmann brains are possible, even in principle, how can we ever trust our observations? After all, you could be one right now, imagining this script as part of an elaborate phantom reality. Philosopher Nick Bostrom frames it as a skeptical hypothesis. We can't disprove that everything we know is a glitch in an indifferent cosmos, the unsettling truth. Science assumes our perceptions reflect objective reality, but Boltzmann brains throw that assumption into crisis. Yet there's a twist. The very fact we're having this debate might be evidence against the paradox. For a Boltzmann brain to ponder its own existence, its hallucinated world would need astonishing internal consistency, laws of physics, historical records, even the memory of reading this sentence. That level of order is even more improbable than the brain itself. Some physicists argue this recursive absurdity collapses the paradox from within. If randomness can't explain our orderly experience, maybe the multiverse isn't as lawless as we thought. The takeaway isn't just philosophical whiplash, it's a stark reminder of how fragile our grasp on reality might be. Whether the paradox discredits the multiverse or highlights fine-tuning, one thing's certain: the universe's deepest mysteries aren't just out there. They're woven into the fabric of our own consciousness, begging the question, are we the rule or the exception? What if numbers aren't just tools we use to describe the universe? What if they are the universe? That's the radical proposition at the heart of Max Tegmark's mathematical universe hypothesis. Forget equations as mere approximations of reality. Imagine instead that existence itself is math, that stars, atoms, even consciousness are just intricate structures in an abstract, eternal landscape of numbers. It's like discovering the world isn't made of matter, but of music, and every galaxy, every thought, is a note in an endless symphony of pure mathematics. Take something as simple as the number pi. We learn it as the ratio of a circle's circumference to its diameter, about 3.14159, and so on infinitely. But Tegmark would argue pi isn't just a handy constant, it's a place. A universe where circles exist must contain pi, just as ours contains hydrogen or gravity. Now stretch this further. Every possible mathematical structure, from geometric shapes to hyperdimensional manifolds, exists as a physical reality somewhere. Our cosmos, with its 3 spatial dimensions and quantum fields, is just one equation in an infinite library. In this view, planets aren't made of math. They are math-specific configurations in a grand computational fabric. The implications are dizzying. If reality is mathematics, then the laws of physics aren't legislated by some external force. They're inevitable truths, like 2 + 2 = 4. Gravity behaves the way it does not because of some cosmic decree, but because it's the only way space-time can consistently curve in a 4-dimensional manifold. Even time might be an illusion, just a particular axis in a static mathematical object, with past, present, and future eternally fixed like points on a graph. Critics push back with a gut-level objection. Math feels intangible, abstract. How can symbols in a notebook be the stuff of reality? Tegmark's counter is disarmingly simple. What's more fundamental, the quarks in your brain or the mathematical patterns describing their interactions? Every scientific breakthrough, from Newton's gravity to quantum mechanics, reveals a universe that follows mathematical rules with eerie precision. The shocker, Tegmark says, isn't that reality obeys math, it's that we ever thought it could be otherwise. But here's the twist that bends the mind. If every mathematically possible structure exists, then universes with different math must too. Imagine a cosmos where parallel lines eventually meet, or where prime numbers behave erratically. These aren't just thought experiments, they're places, as real to their inhabitants as our universe feels to us. The chilling beauty, we'll never visit them because the math governing their physics wouldn't permit stable brains like ours to form. We're trapped in the tiny slice of mathematical space where our kind of consciousness can arise, another form of cosmic fine-tuning, but with numbers as the architects. The hypothesis forces a profound question. Is mathematics discovered or invented? Most scientists assume we're uncovering pre-existing truths, like explorers mapping uncharted terrain. But if Tegmark's right, the terrain is the math, and we're not just cartographers but characters drawn on the map itself. When Einstein said, "The most incomprehensible thing about the universe is that it's comprehensible," he might have been hinting at this eerie alignment between human logic and cosmic order. Maybe the reason math works so well isn't because we're clever, it's because we're made of the same stuff. So next time you see a rainbow, remember, you're not just observing wavelengths of light. You're witnessing a fractal in the grand equation of existence, one that writes itself into being every moment. The universe isn't described by numbers, it dances to them. And in that dance, every spinning electron, every distant supernova is just mathematics finding its voice. Earth doesn't just orbit the sun, it rides a razor's edge of cosmic luck so improbable it beggars belief. Start with the Moon, a celestial oddball so massive relative to our planet that its gravity acts like a stabilizer, preventing Earth's tilt from veering wildly over millennia. Without that steadying hand, our climate would lurch between extremes, turning continents into Arctic tundras or scorching deserts within generations. Next, plate tectonics, the slow dance of continents that recycles carbon, regulates temperatures, and fuels volcanic soil renewal. Mars, frozen and geologically dead, shows what happens when that engine stalls. Even Jupiter plays bodyguard, its immense gravity deflecting asteroids that might otherwise pummel Earth into extinction. Then there's water, not just its presence, but its bizarre properties. Unlike most substances, ice floats, insulating oceans so life can survive beneath. Water's ability to dissolve almost anything makes it the universal solvent for biochemistry, while its surface tension allows trees to defy gravity, pulling water hundreds of feet upward. Even the Sun's quiet reliability is a fluke. 90% of stars in our galaxy are volatile red dwarfs, prone to lethal flares that would sterilize nearby planets. This isn't just a checklist of habitable traits, it's a cascade of perfect accidents. Astronomer Frank Drake quantified the odds in his famous equation, multiplying variables like star formation rates and the fraction of planets with life. The result, even optimistic estimates suggest intelligent civilizations should be vanishingly rare. Yet here we are on a planet that checks every box with eerie precision. So is Earth a statistical miracle or proof the deck was stacked? The multiverse answer would shrug. With infinite tries, even a 1 in a trillion shot becomes inevitable. But others see a different story, a universe where the constants of physics and the quirks of planetary science align like gears in a machine designed to produce thinking beings. Whether by chance or choice, one thing's clear: we're standing on the most improbable real estate in the cosmos, a world so finely tuned it feels less like a roll of the dice and more like a masterpiece. What if the universe's fine-tuning isn't a puzzle to solve, but a sign we've been missing a deeper layer of physics? Enter loop quantum gravity, a radical rewrite of reality where the fabric of space-time isn't smooth and continuous, but woven from tiny, indivisible threads like a cosmic tapestry stitched together at the smallest scales. Picture a playground seesaw. In our everyday world, it balances perfectly when both sides have equal weight. But zoom into the quantum level and the seesaw starts flickering, its planks dissolving into a frenzied dance of discrete steps. Loop quantum gravity suggests that beneath the apparent smoothness of gravity, space itself operates in these jagged quantum jumps, eliminating the need for arbitrary fine-tuning by building balance into the universe's very structure. This isn't just abstract math, it rewires how we think about cosmic constants. Take the cosmological constant, that infamous number that's fine-tuned to 1 part in 10 to the power of 120. In loop quantum gravity, its value might emerge naturally from the way space-time quantizes, like how the pitch of a musical note depends on the length of the vibrating string. No need for multiverses or divine dial twisting. The math might simply forbid certain extreme values, locking physics into life-friendly parameters by default. It's as if the universe has built-in guardrails, preventing it from veering into chaos. String theory offers another escape hatch from fine-tuning. Imagine the universe's forces as instruments in an orchestra. In our current model, each instrument is tuned by hand to precise frequencies, hence the apparent fine-tuning. But string theory suggests these instruments are actually different vibrations of the same underlying strings, their harmonies dictated by deeper symmetries. The apparent precision isn't arbitrary. It's the inevitable outcome of a unified framework where gravity, electromagnetism, and nuclear forces are just different notes in the same cosmic chord. Yet these theories come with trade-offs. Loop quantum gravity's granular space-time might solve fine-tuning, but it struggles to explain why our universe has 3 spatial dimensions instead of 2 or 7. String theory's elegance is shadowed by its need for 10 or 11 dimensions, most of which are curled up so tightly we'll never perceive them. Critics argue these aren't solutions so much as relocations, moving the mystery from why these constants to why these hidden rules. But the boldest challenge to fine-tuning comes from causal dynamical triangulations, a model where space-time assembles itself from microscopic building blocks like a cosmic Lego set. Run the math and something astonishing happens. A 4-dimensional universe resembling ours emerges naturally from the chaos, no delicate tuning required. It's as if reality self-organizes, with complexity arising from simple parts like how a kaleidoscope creates intricate patterns from a handful of colored beads. The takeaway: fine-tuning might be a mirage, a byproduct of our limited perspective. Just as Newton's laws seemed absolute until Einstein revealed their relativity, our current physics might be a local snapshot of something far grander. Whether through loops, strings, or cosmic Lego, the answer to the universe's perfection may not lie in chance or design, but in the discovery that it was never fragile to begin with. Long before telescopes or quantum equations, humanity's oldest stories whispered of realities beyond our own. The ancient Hindu Rig Veda, written over 3,000 years ago, speaks of innumerable universes drifting like bubbles in foam, each with its own gods and laws, a striking parallel to today's inflationary multiverse theory. Norse myths envisioned Yggdrasil, the world tree, whose branches held 9 separate realms from Asgard's gleaming spires to the frostbitten wastes of Niflheim. These weren't just fantasies, they were intuitive grasps at a truth science would only articulate millennia later, that our world might be one thread in a vast, tangled tapestry. Greek philosopher Anaximander took a different approach, proposing the apeiron, an infinite, boundless source from which countless worlds emerged and dissolved like waves on a shore. Fast forward to the 12th century, and Islamic scholar Fakhr al-Din al-Razi speculated about 1,000 worlds beyond this one, each governed by its own nature. Even indigenous Australian Dreamtime stories described a time before time where ancestral spirits shaped multiple layers of reality. What's haunting isn't just the similarity of these ideas, it's that they arose independently, as if the multiverse were an archetype buried deep in human consciousness. The leap from myth to math began in earnest with philosopher Gottfried Leibniz in the 17th century. His possible worlds theory argued that every logical alternative to our universe must exist somewhere, a thought experiment that eerily foreshadowed quantum superposition. But the true turning point came in 1957, when physicist Hugh Everett Roman III reimagined reality itself. While others dismissed quantum oddities as measurement glitches, Everett asked, what if every quantum decision does play out just in branches we can't see? His many worlds interpretation wasn't metaphysics, it was a direct consequence of Schrödinger's equation, treating wave function collapse as an illusion. In Everett's cosmos, every choice spawns new universes, each as real as our own. What's fascinating isn't just how often multiverse ideas recur, it's why. Perhaps grappling with infinity is hardwired into us, a cognitive itch we've scratched through both myth and equations. Or maybe these recurring visions hint at something deeper, that across time and culture, humanity keeps stumbling toward a truth too big for any single era to hold. Whether through the world tree's branches or Everett's branching wave functions, the message is the same. Reality might be far stranger and grander than it seems. For centuries, Occam's razor has sharpened scientific thinking, the idea that the simplest explanation is often the best. But when it comes to the multiverse versus intelligent design, this philosophical blade cuts both ways in unexpected directions. Picture a courtroom where these two theories stand trial. On one side, the multiverse defense argues its case. Your Honor, we don't need a cosmic designer to explain fine-tuning. Infinite universes mean every possible configuration exists. Ours just happens to be the lucky one. It's a sweeping argument, elegant in its simplicity, but the prosecution pounces. Then where's your evidence? You're invoking an infinite number of unobservable worlds to avoid one unexplained variable. That's not Occam's razor, that's Occam's chainsaw. The debate hinges on what we consider simple. A designer introduces a new entity, some intelligent force setting the dials. But the multiverse introduces something arguably more staggering, an endless proliferation of entire realities, each with its own physics. Which is the heavier burden? Philosopher Richard Swinburne frames it like this. If you find a single sentence written in the sand, do you assume a random scribble from infinity matched those words or that someone wrote it? The multiverse asks us to embrace cosmic bulk buying, an everything everywhere, all at once approach where fine-tuning dissolves into statistics. Design asks us to consider intention behind the numbers. But here's where the metaphor twists. Science thrives on falsifiability, the ability to test claims. The multiverse, for all its grandeur, struggles here. As physicist Paul Davies puts it, invoking an infinity of unseen universes to explain the one we see is like using a magic charm to ward off dragons. It works, but only if you ignore why it shouldn't. Meanwhile, design offers intuitive appeal but risks halting inquiry. If we say a designer did it, do we stop searching for deeper mechanisms? Yet both theories share a deeper irony. The multiverse, often framed as the naturalistic alternative, requires a leap of faith worthy of theology, belief in realms forever beyond observation. Design, often labeled unscientific, mirrors the physicist's quest for elegant underlying principles. Perhaps the real crime isn't complexity or mysticism, but prematurely closing the case. After all, history shows the universe rarely fits our courtroom metaphors. It's more likely to surprise us than obey our rules of thumb. Imagine the universe not as a carefully tuned machine, but as a murmuration of starlings, a swirling, self-adjusting dance where complexity emerges not from blueprints, but from simple rules playing out on a cosmic scale. This is the heart of emergent universe theories, where the exquisite fine-tuning we observe might not be preordained, but an inevitable outcome of deeper, more fundamental processes. Think of how snowflakes form, no two alike, yet each perfectly symmetrical, their intricate patterns arising from the basic physics of water molecules and temperature gradients. Could the cosmos work the same way? Its laws not handed down from above, but crystallizing from the chaos like frost on a window pane. One provocative approach comes from fractal cosmology, which sees the universe's large-scale structure, the vast web of galaxies and voids, as a natural consequence of iterative processes. Zoom into a fractal like the Mandelbrot set, and you'll find the same intricate patterns repeating at every scale, generated by a single equation fed back into itself. Astrophysicists like Laurent Nottail suggest space-time itself might behave similarly, with galactic clusters mirroring the branching of neurons or river deltas. In this view, the universe's apparent fine-tuning isn't magic, it's mathematics in motion, complexity blooming from simplicity. Then there's the crystallographic model, where cosmic evolution mirrors the growth of a crystal. When a solution cools, molecules spontaneously align into repeating lattices, their structure dictated by underlying symmetries. Analogously, the early universe's cooling might have frozen out the laws of physics we know, like ice forming in a particular crystal pattern. MIT's Jeremy England frames this as dissipation-driven adaptation, systems naturally evolving to disperse energy more efficiently, much like how a candle flame shapes itself to burn optimally. Stars, galaxies, even life itself could be nature's way of smoothing out energy gradients, no fine-tuning required. The most radical twist, thermodynamic selection. Just as Darwinian evolution favors traits that enhance survival, universes might select for stable configurations over time. Physicist Lee Smolens's cosmological natural selection posits that black holes could birth new universes with slightly tweaked physics, creating a cosmic lineage where life-friendly parameters gradually dominate. It's survival of the fittest, but for space-time itself, where our universe's constants aren't fine-tuned, but naturally honed across generations. Critics argue these theories exchange one mystery for another. If complexity emerges from simplicity, where do the foundational rules come from? But their power lies in reframing the question. Instead of asking why the universe seems designed, we might ask how inevitability masquerades as intention. Like watching a river carve its own canyon, the beauty isn't in the endpoint, it's in realizing the endpoint was always in the water's nature. The universe's perfection, then, might not be a stroke of luck or a sign of craft. It might just be what happens when existence has enough time to find its own rhythm. What if the tables are turned, not us observing the universe, but the universe emerging from the act of observation itself? Radical idealism flips the script on reality, suggesting that the cosmos isn't a physical construct but a mental one, a vast projection of consciousness. Think of it like this: when you play a video game, the graphics aren't the real world, they're an interface, a simplified representation your brain can navigate. Cognitive scientist Donald Hoffman takes this further with his interface theory, arguing that evolution shaped our senses not to reveal objective truth but to hide it. The trees, stars, even space and time, they might be nothing more than a user-friendly dashboard, masking a reality far stranger than we can perceive. This isn't just philosophy, it's a challenge to physics. If consciousness creates reality, then the multiverse could be less like bubbling universes and more like overlapping dreams, each layer a thought in some vast mind. Quantum mechanics already hints at this. Particles exist in superposition until observed, as if reality waits for a viewer to make up its mind. The many worlds interpretation might not need infinite branching universes, just infinite possibilities in a single, malleable mental field. Even time could dissolve into a series of nows, with past and future just artifacts of how consciousness sequences experience. Hoffman's theory collides with the multiverse in eerie ways. If space-time is an illusion, then parallel worlds might not be out there but in here, different projections of the same underlying consciousness. Imagine tuning a radio. Each station exists simultaneously, but you only hear one at a time. Similarly, alternate realities could be frequencies of awareness, normally out of phase but occasionally bleeding through as déjà vu or glitches in perception. The Matrix got one thing right: the world we see is a construct, but the architect might not be machines, it could be the structure of perception itself. Skeptics bristle at the lack of a mechanism. How does mind conjure matter? Yet idealism has a surprising ally in physics: quantum entanglement. When particles remain connected across vast distances, interacting instantly, it suggests a deeper unity beneath the illusion of separation. Even the Big Bang singularity, a point of infinite density where all distinctions vanish, mirrors the idealist's one mind from which multiplicity arises. The universe's fine-tuning might not be accidental or designed, but inevitable, the only possible outcome when consciousness tries to imagine something other than itself. The chilling beauty of this idea, it dissolves the line between observer and observed. You're not just in the universe, you are the universe experiencing itself from a particular vantage point. The multiverse becomes less a cosmic accident and more a kaleidoscope of perspectives, each turn revealing a new facet of the same infinite whole. Whether through Hoffman's interface or the quantum void, the message is the same. Reality might be the ultimate virtual machine, and we're both the players and the code. If the multiverse teems with countless universes, some harboring civilizations far older and wiser than our own, why does the cosmos feel so silent? The Fermi paradox, which asks why we haven't found evidence of extraterrestrial life, might hold unexpected clues when applied to the multiverse. Picture a sprawling library where every book is a self-contained universe. Even if most are empty or chaotic, a few surely contain beings capable of cosmic engineering. So where are the echoes of their existence? The chilling answer might lie in theories originally crafted for alien life, now stretched to terrifying new scales. Take the zoo hypothesis. On Earth, we observe animals in nature reserves without interfering. Could advanced civilizations be treating us the same way? In a multiverse context, this idea twists into something even stranger. What if other universes are aware of us, but deliberately avoid contact to preserve our natural development? The cosmic equivalent of scientists in white gloves, peering at our universe through some higher dimensional microscope without disturbing the experiment. The silence wouldn't be a mystery, it'd be policy. Then there's the dark forest theory, popularized by sci-fi writer Lou Sixon. Imagine every civilization is a hunter creeping through a pitch-black woodland, terrified of revealing their location. In such a universe, broadcasting your presence is suicide. The moment you're detected, a more advanced power might strike preemptively to eliminate competition. Now scale this up to the multiverse. If traversing between realities is possible, the first rule might be stay hidden. Any universe that leaks signals, whether through gravitational ripples or experiments piercing the dimensional veil, could attract existential threats beyond comprehension. But the paradox might cut deeper. What if the silence isn't deliberate but inevitable? Civilizations could hit a technological ceiling long before mastering multiverse travel. Think of ants trying to comprehend the internet. Some gaps might be unbridgeable, no matter how advanced a species becomes. Or worse, the laws of physics in our universe might be a prison, meticulously configured to prevent escape. Like a fish unaware it's in a tank, we might lack the very tools needed to detect or interact with other realities. Sci-fi offers eerie parallels. In the Twilight Zone, a race of hyper-intelligent beings dismisses Earth as a trivial speck until they realize humans have begun probing dimensions beyond their own. Star Trek's Prime Directive forbids interfering with less developed worlds, mirroring the zoo hypothesis. Even Rick and Morty plays with the idea that infinite realities render individuality meaningless, making contact pointless. These stories hint at a truth science is just beginning to grasp. In an infinite multiverse, the greatest mystery might not be why we're alone, but why we'd ever expect to not be. The unsettling takeaway: absence of evidence isn't evidence of absence. Other universes or their architects might be all around us, watching, waiting, or simply indifferent. Or the darkest possibility of all: we're not just alone in this universe, but in all of them, the sole flicker of awareness in a void that never needed us to begin with. Either way, the silence isn't empty. It's a mirror reflecting our deepest fears about what or who might be out there. Accepting the multiverse wouldn't just rewrite textbooks, it could ignite a technological revolution unlike anything we've seen. Imagine harnessing the very fabric of reality, not just within our universe but across the infinite ensemble of them, one of the most radical possibilities. Vacuum decay manipulation. Right now, our universe exists in a metastable state, a valley in the energy landscape of physics. But quantum theory suggests a lower energy valley might exist, and if triggered, a bubble of true vacuum could expand at light speed, rewriting the laws of physics as it moves. Terrifying, absolutely, but if we could control it, we might wield it like a cosmic scalpel. Picture engineers inducing localized vacuum decay to create pockets of space with custom physics regions where gravity is weaker for anti-gravity propulsion, or where light moves faster, enabling interstellar travel. The catch: one miscalculation and the bubble doesn't stop. It's the ultimate high-stakes engineering. Build a warp drive or erase existence itself. Now stretch the idea further: universe-hopping technology. If other realities exist beyond our cosmic horizon, could we bridge the gap? Some models suggest quantum entanglement might hold the key. particles linked across dimensions, acting as anchors for traversal. Imagine a device that doesn't move through space but rotates into a higher dimension, emerging in a parallel world where the laws of physics are just different enough to be transformative. Need unlimited energy? Jump to a universe where perpetual motion is possible. Facing ecological collapse, harvest resources from a reality where Earth never industrialized. The ethical dilemmas here are staggering. Is it colonization if you're tapping into a world where humans never evolved? What happens when we meet versions of ourselves who made different choices? Do they have rights, or are they just raw materials for our survival? And then there's the simulation angle. If we're living in a construct, could we hack our own code? Future civilizations might not just discover the multiverse. They could program it, writing new universes into existence like software forks. The moral weight of that power is incomprehensible. Every glitch we fix, every parameter we tweak could erase entire branches of conscious experience. Would we become gods or prisoners of our own creations? The line between physics and philosophy blurs when the tools to reshape reality are on the table. This isn't just speculative fiction, it's the logical endpoint of taking multiverse theories seriously. The same science that paints us as cosmic accidents could one day hand us the keys to the cosmos. But with that power comes a question humanity has never faced before. How do you ethically navigate an infinity of possibilities when every choice spawns a new world? From the neon-soaked chaos of everything everywhere all at once to the serene cosmology of Buddhist teachings, humanity's obsession with alternate realities isn't just a modern quirk. It's a thread weaving through our stories, faiths, and deepest existential questions. Take cinema first. Hollywood's multiverse explosion isn't just Marvel spectacle. It's a mirror for our fractured, hyper-connected age. In Everything Everywhere, the protagonist Evelyn doesn't just hop dimensions. She's crushed by the weight of infinite selves, each choice branching into lifetimes of regret and possibility. The film's genius lies in making quantum physics visceral. Bagel-shaped black holes symbolize nihilism, while googly eyes become tokens of meaning in the chaos. Compare this to Doctor Strange's kaleidoscopic battles or Rick and Morty's nihilistic escapism, and a pattern emerges. These aren't just plots, they're coping mechanisms for a world where identity feels fluid, where the internet splinters us into endless digital personas. The multiverse in film becomes a metaphor for the modern condition. Overwhelming, boundless, yet oddly comforting in its promise that somewhere another version of us made the right choice. Religion has danced with these ideas for millennia. Buddhist cosmology describes Trisahasra, a universe of 3,000 realms from heavenly abodes to hellish tortures, each reflecting the karma of its inhabitants. Unlike Western linear narratives, this is a cyclical multiverse where souls transmigrate endlessly until enlightenment breaks the wheel. Hindu texts like the Puranas speak of innumerable Brahmandas, egg-shaped universes, each with its own Brahma crafting unique realities. Even Christianity's medieval mystics like Hildegard of Bingen envisioned layered heavens, while indigenous Australian Dreamtime stories describe parallel spiritual dimensions overlapping our own. What unites these traditions? Not just imagination, but a shared intuition that reality is vaster than our senses reveal, and that our lives are but one verse in an epic poem spanning dimensions. Philosophy's take is more razor-edged. Leibniz's Possible Worlds argued that every coherent alternative to our universe must exist, a notion that quantum physics later echoed. But Nietzsche's eternal recurrence terrifies on a personal scale. What if you're doomed to relive your life, identical in every detail, infinite times? Camus rebelled against this absurdity, while contemporary philosophers like David Lewis treat parallel worlds as concrete entities, not metaphors. The through line, whether through equations or allegory, we're haunted by the same question. If reality is plural, what weight do our choices hold? A single life feels monumental in a lone universe, but in a multiverse, every triumph and failure is duplicated endlessly, either diluting meaning or amplifying it through repetition. This cultural tapestry reveals something primal. From ancient shamans to TikTokers, we've always sought escape hatches from our singular existence. The multiverse, whether framed as sci-fi or scripture, is the ultimate what-if, a salve for regret, a challenge to free will, and perhaps a reminder that the boundaries of reality were always more porous than we dared to believe. The next decade could rewrite cosmology's rulebook, with experiments poised to crack open the multiverse debate like never before. At CERN, scientists aren't just smashing particles, they're hunting for hidden dimensions. The Large Hadron Collider's next upgrade might detect microscopic black holes, fleeting evidence of gravity, leaking into other universes through higher dimensional brains. Even more tantalizing are plans to probe the quantum foam of space-time itself, where fluctuations at the Planck scale could reveal whether our universe is one thread in a grander weave. Imagine photographing the fabric of reality at a resolution so fine, you'd see the stitches holding dimensions together. Meanwhile, quantum gravity experiments are pushing beyond theory into tangible tests. The Einstein telescope, a next-generation gravitational wave observatory, could catch echoes from the Big Bang's first trillionth of a second, a window into whether our universe's inflation was a one-time event or part of an endless cycle of cosmic births. Tabletop experiments with supercooled atoms are even hunting for deviations in gravity at microscopic scales, anomalies that might betray the influence of parallel worlds tugging at ours from just beyond perception. It's like feeling the draft from a door you can't see, hinting at rooms beyond your own. Then there's the cosmic microwave background, the afterglow of creation. Future space telescopes like Light Bird will scour its polarization patterns for bruises, subtle imprints left by collisions with other universes in the multiverse's froth. Some theories predict these fingerprints would manifest as cold spots or swirling vortex patterns in the radiation, like finding someone else's fingerprints on what you thought was your private property. Other teams are developing quantum sensors so precise they could measure whether fundamental constants truly are unchanging, or if they drift imperceptibly across space, a smoking gun for patchwork physics stitched together from multiple realities. The stakes within our lifetime, we might have hard data to confront the ultimate question: is our universe a solo act or one note in a cosmic chorus? Whether through particle collisions, gravity waves, or quantum whispers, science is building the tools to listen for the echoes of other worlds. The answers won't just settle a theoretical debate, they'll redefine what it means to exist at all. So as we stand at the edge of this cosmic labyrinth, one inescapable question lingers: are we stardust scattered by chance across the roulette wheel of infinity? Or is the universe humming a melody so precise, so intentional, that it can only be the work of a master composer? The multiverse theory offers cold comfort in numbers, where our existence is just one possible outcome in an ocean of failed realities. Yet the fine-tuning argument whispers of something more, a cosmos where the constants cling to their values with eerie devotion, as if holding their breath to keep us alive. Picture the universe as a grand cathedral. The multiverse view sees it as one chapel among endless others, some in ruins, some never finished. Ours just happens to have the right acoustics for life's echo. The design perspective: this isn't just a building, it's a sacred geometry, every arch and angle calculated to sustain the fragile flame of consciousness. Neither answer is small. One makes us a statistical accident, the other places us at the heart of a mystery spanning dimensions. But here's the truth that unites them both: we're here, thinking these thoughts, tracing the contours of the unknown. Whether through infinite rolls of the dice or the steady hand of some cosmic architect, the universe has conspired to create beings who can gaze back at it and ask, why? That alone is staggering, so we leave you with this: next time you look up at the night sky, don't just see stars, See the debate raging in every photon, randomness or design, accident or intention. The answer might change how you walk through this world. If your mind's buzzing with possibilities, you're not alone. Hit subscribe. We're just getting started on unraveling reality's deepest riddles. The universe or multiverse isn't done surprising us yet.